that brings us to Newton's first law. Okay, so we've had a little primer on what forces are, how they're defined, and what kinds of forces we can expect to see. Now we'll talk about Newton's laws. And what are Newton's 3 laws? Does anybody remember or know them offhand? I'm going to start bringing gold stars or something, or candy. Actually, I used to bring candy around Halloween because I always have lots of candy. And I would throw it to people when they answered questions until I nailed a student in the front row in the face. And then I stopped throwing candy at people. He was okay, and he got to keep the Skittles, but it's kind of bad. So anyway, Newton's 3 laws. Anybody got Newton's first law? Yeah.
An object in motion stays in motion unless acted on another force.
Yeah. So an object in motion stays in motion. This is the basic definition. Things move unless acted on by a force, right? Or they don't move unless acted on by a force. Okay. We'll go into the full hardcore physics definition of that, but the principle is the same. Anybody know Newton's second law? Yes.
Energy cannot be created or destroyed?
No, but that's a good physics law.
Okay.
Yeah. Yeah.
I don't know it, but is this in relation to thermodynamics by any chance? Because I think that's what he said.
Yes, this isn't, but that is. That's almost like the golden law of physics. Except it's not totally true, because it turns out energy can be converted back and forth from mass, which is neat. But yeah, if you're interested in that, take the 3rd semester of this class. We talk about that in detail. That's you know that whole equation that everybody knows, E equals mc squared. The E is energy and the m is mass, and c is the speed of light. So it says if you have mass, it could be energy, or if you have energy, it can be mass. And yeah, if you've ever had a PET scan, that's actually an example of converting mass and energy. Anybody know what a PET scan is? Oh, okay, never mind. Well, it's not a good example, but yeah, we'll talk about that later. Okay, so Newton's second law. We've gotten off topic. Okay, well, it's the only other equation people know about physics, which is force equals mass times acceleration. Because remember, we were saying when you have acceleration, it comes from force. That's the equation that relates them. It's a super simple equation with only 3 variables, really easy to remember, and it's going to haunt your life for the next 4 weeks. And probably longer, actually. But we're going to focus on that. It's going to be the core of almost all the problems we do. What about the 3rd law? How many of you took high school physics? Oh, so only you should be ashamed. Okay, or your teacher from high school. The 3rd law is every action has an equal and opposite reaction. That's the basic way of saying it. But really, it talks about force pairs, right? So if like what I was talking about, when I push these things together, there's normal forces. There's a force from this on this, and a force from this on this, and they should be equal, okay? Because otherwise, you'd move. All right, and okay, so those are the Newton's 3 laws. I learned them when I was 5 in the car, because my mom would just quiz me on science stuff in the car, because that's how you end up a physics professor apparently. But yeah, she was a chemist, but then she became an elementary school teacher, so she was perfectly suited for that. Okay. Newton's first law. Let's talk about this. So here's an air hockey table, which is one of my favorite games, and none of my children have beaten me yet, so that's really the key of my success in life. Okay, here's what are those little puck things, and what's interesting about an air hockey table? It slides because it has very low friction, and the way that we do that is you sort of lubricate the table. The fluid in this case is air, so it shoots a bunch of little air things up, and that means the little puck is sort of floating, and therefore it doesn't have a lot of friction. Okay, it's not in contact with the surface. So here's our little air hockey table. What happens if nothing hits the puck? Assuming a perfectly designed air hockey table. It just stays there forever. Okay, it'll waste energy just pumping air under it, but it won't move. Okay. What happens if you give it a little tiny tap? It'll move. But how will it move? Does it move in a swirly?
No.
No? What's the shape of its motion? Straight. It's going to move in a straight line. Is it going to speed up or slow down?
Slow down.
Assuming no friction. Yeah, it should stay at the same speed when we have no friction. And it'll do that until it hits something, right? So the only time it changes direction is when it hits the wall. If you had an infinite air hockey table and it was perfectly frictionless, and you gave the puck a tap, it would just go in a straight line at the same speed forever, okay? Which is a weird thing to think about. But you can kind of do this in space, which is neat. So the puck keeps moving until something stops it or changes its direction, and that means it has to come into contact with something else or interact with a long-range force like gravity, okay? So Newton's first law, I found this really great GIF of Newton as a bobblehead. So a body in motion stays in motion, a body at rest stays at rest. We call this inertia. Inertia is just a fancy word that means the same thing. Basically, it means like you need force to move mass, okay? So anything with force needs mass to move it. Inertia is the tendency of an object to resist acceleration, meaning like, if you want to like have like a personal experience with that, like when you're in bed and you don't want to get out of bed, you need like some force and energy to get you out of there. Mass measures how much inertia an object has. And so what we mean by that is people sometimes misconstrue this with gravity because we have a lot of personal experience with gravity from like living on a planet that has gravity. So, but what I mean by inertia is even if you take a bowling ball and you shake it back and forth in space, let's say you end up like out in the middle of space, hopefully with some sort of oxygen and like pressure suit, but and you shake a bowling ball back and forth with no gravity, right? It's still going to take force from you and energy. You'll still have to exert your muscles to move the bowling ball, okay? So it's always going to take force and also therefore energy, which we'll talk about later, to move mass, okay? And here's a little, well, this is a tip, sort of remember, things stay there, and unless you have a force, and in this case, when you're pulling a tablecloth out from under things, if you can get it to not have enough friction by pulling it the correct way, things don't move. So here's our little example.
So that's where this goes on top, and this
guy is not recommended.
Is right up here like this.
Oh, there's no way.
There's a strong possibility that this is not going to work, all right? But it's okay. We got to see your first one, and we'll cut all the rest out, all right?
Oh, gee.
Are you ready for this?
Is it me?
Yeah. Yeah, again, it's not me, all right? All right, so I'm going to move you down just a little tiny bit. I think you're going to be great,
set me
right?
up for success
so you're going to be here like this,
all right.
and your hands are tight, straight down to your toes.
Okay.
Got it?
All right.
Straight down to your toes. No hesitation at all.
All right, okay.
All right,
Miss
ready?
Christensen is
Little
ready to
drum
exit
roll.
the studio.
I'm gonna count you in. Ready? 3, 2, 1, hard.
Okay, so what's happening here? Even though there's something moving out from under it, he's putting force on the cloth, but as long as there's not very much friction between the cloth and the table and the cup, or the plate, then this isn't actually going to move. You're not applying very much force to this object, and everything stays where it wants to stay. So things like to stay where they are. They like to keep doing what they're doing. And so if we want to define this in English in a more physicsy way, when we say a body in motion stays in motion, what we really mean is if we don't introduce any new forces, the object just moves in a straight line at a constant speed forever. Okay? If we don't introduce new forces, you just keep going in a straight line at a constant speed. If you happen to not be moving, okay, and you don't introduce new forces, you just stay there forever. Okay? This doesn't come up very often, but it could. Okay? And when we talk about equilibrium, this is a new term we're going to come up with. Equilibrium says, basically, static equilibrium is the easiest one. You're not moving. So that means your velocity is 0, your acceleration is 0, your net force is 0. Okay, that's static equilibrium. It's the simplest one. But we also have something called dynamic equilibrium, and dynamic just means moving, where you have a constant speed, but your change in speed is 0, meaning your acceleration is still 0, and your net force equals 0. So what we mean by equilibrium is really that we don't have acceleration, that our acceleration is 0, and therefore our net force is 0, because that means the same thing in physics. Because in order to have acceleration, you have to have force. Okay? All right, let's try another problem. It's a clicker heavy day. Okay, we're mostly thinking A. Please discuss, and we'll vote again. We'll take about 30 seconds because we seem to mostly agree. All right, one vote for E. Yes, the answer is going to be A. Let's see, get it back over here. So why? Why is the answer A?
Because it's frictionless. There's no other forces on it.
Yeah, it's frictionless, right? So there's no forces. It starts at 20 meters per second. That's its initial velocity. And because there's no forces acting on it, there's nothing to slow it down, speed it up, or change its direction, okay? So it's going to continue to move at 20 meters per second until it runs into something, okay? All right. So let's talk briefly about reference frames. Okay. So here's a definition. Reference frames are basically just coordinate systems. They extend to infinity in all directions. So if you have X, Y, Z, that's a reference frame. And experiments are people taking measurements, okay? So let's talk about an inertial reference frame because we just talked about inertia. An inertial reference frame is one for which Newton's first law is valid, okay? That means no force or acceleration. And the way you want to think about this is an inertial reference frame. Think about being in a car. Now, it's not safe, but think about being in a car with all the windows covered, okay, if you're moving at a constant speed, all right? And you want to, an inertial reference frame would be like if the person driving the car basically just drives at a constant speed. And the reason for this is if you have a coffee cup sitting on your dashboard or like any part of your car, if you have an inertial reference frame, the coffee will just stay there, okay? How would you tip over? What do you have to do to like tip over the coffee cup? Brake really hard, speed up really fast, or turn, right? If you're trying to keep a liquid stable in your car, then that's what's happening. So if you're in the car and you're moving at a constant speed, and let's say you can't hear what's going on outside and you can't see what's going on outside, can you tell that you're moving? No, right? The only way you'd be able to tell is when you feel the acceleration of slowing down, speeding up, or stopping. So an inertial reference frame is driving in such a way that a cup of coffee on your dash won't spill, okay? A non-inertial reference frame means you can have accelerations, and that gets into sort of general relativity, which is a little bit more complicated, and you need a lot more math to really talk about. So we're going to watch a short video on reference frames just for context. Let me turn the sound back up.
You've probably been on a bus or some other moving vehicle at some point, right? Ever gotten stuck standing up on a bus? Clinging to one of those poles, hanging on for your dear life? Crazy question. What if you were to let go of that pole and jump? What would happen, aside from annoying your fellow busgoers, of course? Let's think. While in the air, your body would not be in any direct contact with the bus, so there's no way that the bus could affect what happens to you. Your intuition may tell you that the bus is no longer moving you forward. So you would, in a sense, stop moving forward, and the back of the bus would crash into you. However unpleasant this obviously seems, it makes sense that it would happen. Except, it doesn't. If you're brave enough and actually do jump on a moving bus, as long as it's moving in a straight line at constant speed, you'll notice that something completely different happens. You land back on the same spot of the bus floor from which you left. Well, that's kind of weird. The bus floor moved forward during your jump. The bus couldn't have pushed you forward while in the air, and yet you still landed in a different spot above the ground? Well, that's just what physicists call inertia, the tendency for an object to maintain its state of motion. All this means is that when an object isn't being pushed or pulled, it continues flying in whatever direction it was going. To paraphrase my high school physics teacher, staying at one speed is just the default. Nothing really causes you to continue moving. You just continue moving because nothing is stopping you. Now let's imagine another scenario. What if you jumped on a moving bus with all the windows sealed shut? As long as the bus doesn't turn a corner, go over a bump, or change its speed. If you jumped, it would just seem like the bus wasn't moving at all. In fact, if you tried to do any physical experiment inside this isolated cabin, none of them could tell you that you were moving, even if a friend on the sidewalk could clearly tell you so. By the way, this friend of yours is always late for the bus. In the time your friend is waiting for the next ride, he has some time to kill, so you tell him to verify the experiments you did on the bus. Surprisingly, he reports the same results that you got. Whether it's your friend at the bus stop or you on a moving bus, the same thing happens. So who is really standing still? Of course, it must be your friend on the ground. He can tell you with the utmost confidence that you're the one who's really moving. Although, you're clever. You can just tell your friend that you're in an equivalent situation and he's the one moving. But this is just childish, right? Although we all can't help but refute our friend's hypotheses just to prove them wrong, we know it deep down that your friend is probably right. It must really be your friend who's standing still. He's on the ground after all. And how can the ground move? It's the ground. But wait, isn't that ground beneath your feet spinning around the Earth at over 300 meters every second? And isn't the Earth orbiting around the Sun at around 30 kilometers per second? And isn't the Sun moving around the center of the Milky Way at over 200 kilometers per second? And yet not you, nor your friend, even notice that you're both moving so fast. Is it even possible to figure out who's standing still at all? The surprising fact is that no, there is nothing you can do to convince everybody, regardless of their state of motion, that you are really the one who is standing still. All you can say is, hey, every experiment I do makes it look like I'm standing still, regardless if someone else disagrees. If you can say this, you are in what physicists call an inertial frame of reference. All this means is that everything around you seems to behave like you are not moving. In this case, you and your friend are both in your own unique inertial frames of reference. You could each claim the other is moving, but in your own frames you're each standing still. In fact, anyone moving in a straight line with constant speed is in their own unique frame of reference. In each frame, you can treat everything as if you're at rest, even though someone else may disagree. But after some thought, we can't be ones to disagree. We're willing to appreciate that all is the same no matter what side you take, being on the bus or on foot. Both you and your friend are right. You are each standing still in your own way. It just depends on your point of view. Just one last thing though. Don't actually jump while on a moving bus. Real buses turn, start, and stop continuously, which would cause an unfortunate accident.
All right, so it's my longer explanation of what an inertial reference frame is, and that's why the word inertia is important. If you want to understand how the acceleration affects reference frames, that's a whole section of physics called relativity. And that's when you can sort of decide when things, time and space, behave differently by who's accelerating, okay? And there is a key point there. The difference when you start talking about general relativity between the bus and the person standing still is at some point to get to that speed, even though you're going at a constant speed, the bus would have had to accelerate, which means that there's energy put into it and forces. And so then you could actually differentiate between those two reference frames if like one person's aging faster or something like that. For a popular culture treatment of time dilation, please watch Interstellar or take the third semester of this class where we will watch Interstellar. Okay.